Salve a tutti, signore e signori, e benvenuti a questo nuovo video.
Quest'oggi sarà nostro ospite John Caruso.
Un ingegnere della Nasa in pensione.
Se volete restare aggiornati su tutti i nostri video, non vi resta che iscrivervi a Tantum in Colloquio e tutti i vostri dubbi saranno risolti
In un'intervista.
Okay, John, we're going to start with the first question. How did you decide to become an engineer and how you got employed by NASA?
So the reason I became an engineer is I was quite good at math, and I used to, from an early, almost 8th grade, I was advanced in mathematics. And by the time I got to graduating, some of the choices were accounting, which my other brother went into, and that just, accounting didn't quite seem right. Engineering seemed more creative for me. So that was a pretty easy decision. And obviously, once I got into engineering school, I just liked it, and it was a lot of work, but I went right through. What happened in order to get into NASA is I went to graduate school. In graduate school, I chose to do what we call engineering mechanics, but we had a composites expert before all of the composite things were available. So you probably have a composite, you guys don't play golf, but maybe a tennis racket's made out of composite, or a golf club shaft is made out of composite. None of those existed before. And so in early, 1982, I took a fellowship between Akron University and NASA. And through the fellowship, I learned about composites, learned about all the equations, did a bunch of finite element work. And we actually, at the time, finite elements was not a big thing yet. It had just started to be developed over the past previous 10 years. So they made us all develop a element. That was part of our training, is to learn how to develop an element in a finite element analysis. But then I used, as part of my thesis, a finite element and I made a composite. I made a fiber and I made a matrix, and I analyzed it. And my advisor had a set of simplified arithmetic equations that he wanted to verify both experimentally and computationally to see if they were accurate. And so my job was to accurately represent in a finite element model the composite, and his job, my advisor's job, was obviously to make the arithmetic equations match the finite element analysis. And he really didn't have a lot of choice. The way he developed them, they were what they were. And when I went into his office, this is what all advisors do. You show up and you go, well, this is what I got. And he goes, did you check your work? So there's a lot of, oh no, did you believe that? Or even if you checked your work, what does the model look like? Did you use the correct interface between the fiber and the matrix? At any rate, once I completed my master's thesis, NASA hired me, and I was a researcher for about 7 years at NASA.
Which were the biggest difficulties you had to deal with during your work experience at NASA?
So from an engineering perspective, one of the major things that we needed to learn as engineers, not on the research side, but when I transferred into the space side, everything that you designed for space didn't have any gravity. And so you quickly, or maybe not so quickly, learn to think in terms of no gravity. So in your automobile, when you put oil into the top of the engine and it flows through the engine as it runs, it drips down into a pan that you can then pick up and send someplace again. So it's a two-phase system. It's both got air in it and it's got the oil in it. In space, we didn't really have pumps that would pump two phases because, of course, when you have a system like that, there would be air intermixed with the oil. Since air is heavier than oil, even in space, it has more mass, but it doesn't drain anywhere because there's no gravity to pull it someplace. So it just sets there, just like a bubble does. And so if you want to have the oil someplace, you have to have a single phase system. It has to be just oil, no air, and it's got to be a closed system. So actually your veins and artery are a closed system on Earth, believe it or not. Your veins and arteries don't have any air in the blood. It's all liquid. So those are the types of things that you have to think about when you're designing for space. Another thing is the thermal effects in space. Air is a great transmitter of heat. And so you can have a cooling plate on your left side and a hot plate on your right. And you can want to make sure that you cool the hot plate with your cooling plate. In air, it's fine because the heat flows through the air and it also radiates. In space, it only radiates. So if you want to have a good system, you want them in contact. Unfortunately, in the outside space environment, you have something called cold welding in a vacuum, and so you don't want two metal pieces to touch. So the best solution won't work in a space application. And the reason I say it that way is one of the projects I worked on was the International Space Station, and we had batteries that needed to be cooled, and we designed a radiator system that would provide the cooling. So we had a hot plate and a cold plate, and of course they were out in the vacuum of space. So you had to get enough radiation across a bunch of fins, the hot ones and the cold ones, to make sure that it got across. There are other heat transfer problems in space as well. The radiator had a closed loop system of ammonia, but if it partially got shaded or part of it got in the sun, there was many different operating temperatures, and it couldn't freeze. If it froze, it would break the lines because, of course, ammonia doesn't quite expand like water does, but none of the guys on the thermal side ever wanted the fluid to freeze. So we had to make sure that even though one part of the radiator might be liquid, we didn't want the other part of the radiator to go cold. So engineering problems were everywhere on the space station, and of course the ultimate thing associated with each one of these problems on Earth is you could fix a lot of problems on Earth by adding mass or by adding another subsystem, which again adds mass. So our problem in space is we had a limited mass budget, so all of our solutions had to be within that mass budget. So anything that you wanted to fix had to be fixed within the mass budget. It had to be fixed within the utilization budget. In other words, you got so much electricity given to you, so you had an electric usage on orbit because, of course, it wasn't limitless. Of course, you couldn't make too much heat in order to make the space station too hot or too cold, even from the outside. You couldn't put a hole in it, obviously. So everything was a trade-off among a variety of things that you couldn't have, and you needed to manage that budget pretty carefully. When you're managing projects with 1,000 or 2,000 people, which is what we were doing with the International Space Station, communication is really tough. Communication in general is really hard, but when you're communicating around 1,000 people or 2,000 people, you have to be pretty precise about what you do. And then, of course, corporations have their profit motive to take care of. The government gets mad at corporations for taking profits. So we had all of the confusion among people thinking that corporations were trying to rip us off as well as trying to get the work done.
Which were the best moments of your job? Can you?
Almost always it was watching your stuff launch into space. Our launch package for the International Space Station, I believe, launched in 1999. I had not been on the project at that point. My first flight hardware launched on one of the shuttles that had a problem in, must have been 86 or 87. and we were given 3 days to do the work of a 16-day mission, and certain experiments were given priorities, and mine was one of them. So mine wasn't slated to operate until a week after it had launched, but they called me the night that it launched. We flew down the next day, and not only did we watch our hardware launch, but we were also given the opportunity to operate it. So for about 36 to 40 hours off and on, we stayed straight to make sure that all of my stuff got done on that. I was pretty well beat after that in terms of being exhausted, but it was so invigorating that I really couldn't get much sleep during the 36 or so hours or as we were doing that. And then we also designed some rovers that did not go into space, but we were given the opportunity to both test them in our slope facility, which is a big, let's see, it's in meters, if I can do it in meters. It's probably 20 meters. It's a big sandbox. And so we got to run our rovers in the sandbox. We were worried about traction and digging in most of mine. And then I got to go to Hawaii on Kilauea. What's the volcano? And we got to operate our rovers on the mountain as a preliminary test site for a lunar analog. It wasn't a great lunar analog, but it was always cool. So getting to operate your own hardware and having it launch is pretty interesting.
Can you tell us something about the rovers that you built?
Okay, so the Kratos rover was about 1 meter long by 1 meter wide. It had tracks, and it had a bucket that's set about 3, 4, 5 centimeters off of a surface. Mostly, in our case, we were thinking about the lunar application. So we use sand as an analog for the lunar regolith. And so we were basically tasked with digging up the lunar regolith and delivering it to a station so that they could extract oxygen from the lunar regolith. So that was the vehicle's job. Part of our other internal job is we were designing the oven that was going to heat up the regolith to extract the oxygen. We had to get up to about 900 centigrade to do that. So those are 2 projects already. We also had Scarab. Scarab was a rover that was designed for the moon to go up certain inclines, although Kratos went up a higher incline than this other rover did. But its wheels expanded and contracted, and it was also it drove on its own. So before we had self-driving cars, of which Carnegie Mellon did a lot of the groundwork in 2003, 4, 5, and 6, we worked with Carnegie Mellon, who ultimately had a Google interaction and had a connection to GM, and we were working on autonomous rovers. So the idea was we would go to the moon. So we were going to try to give it locations on the moon. Of course, on the ground you could use GPS, but we didn't want to use GPS. And so Scarab would basically drive along the moon, not go in the craters, and not run into boulders, and get where we wanted. In other words, it would drive autonomously if we told it where to go. We gave it kind of points. So that was one thing that we worked on. We were bidding on a Mars mission to extract oxygen from the atmosphere of Mars. What we were trying to do, we were going to bring in CO2, carbon dioxide. We were going to take an oxygen off of that, and then we were going to put out CO, carbon monoxide, and we were going to keep the oxygen. The oxygen in the air on Mars is like 0.4%. So you can think of it as zero, because statistically it's not significant. So one of the things that we had to design was a jet engine, because the atmospheric pressure on Mars was so small that we needed a jet engine to suck in enough air to then take out an oxygen. And of course, the jet engine was, an inch or two long. It wasn't an aircraft jet engine, but it operated just like a jet engine did. It was the coolest thing ever. Honestly, it was really neat. Of course, we never got to build it, but the company had designed these types of little engines for other projects that were utilized at low pressure. All these were at Reynolds numbers and all these other numbers that engineers use that are not very common in utilization on Earth, because of course we have a different pressure regime. Even our airplanes use a different pressure regime. But on Mars, because the pressure was so low and we needed such a high volume, it was a little jet engine that we designed. It was really neat. In terms of the moon, we were asked to dump the regolith into a oven and heat it up to 900 C, take the oxygen off of a ceramic. The moon is largely made up of a oxidized material. That's what the lunar regolith is mostly made of. So if you want to think of something that's oxidized on Earth, think of a piece of metal that's on your car and rust. Rust is with the extra oxygen. The regular metal is without it. And so there's all this stuff that's kind of like rust on the moon. So when you heat it up, it gives off an oxygen, and you can pick it up and you can take it someplace, and then you can dump the regolith out and do it again. So that was another thing that we worked on. Part of my group's work was on seals, and this is one of the reasons why I tell you it's so hard to go to the moon, is because once we dumped regolith past the seal of this little oven, it never sealed again. It's the same thing when we were on the moon with our lunar lander. They opened the door to go out, and they shut it behind them. But when they went back in, the regolith from just the little bit of walking around got around the seal of the door, and it didn't seal again. It sealed enough for them to survive, but it didn't seal perfectly. So seals are a major problem when you go places.
Se vi è piaciuto il video mettete like e condividete. La seconda parte uscirà mercoledì alle 15.